Okay, we have an overhead view of a portion of an exercise machine, and we're told that the tension in this cable is 780 newtons. We want to determine the equivalent force couple system at point B and then at point O. And we're asked to record our answers in vector format. So we have an XY coordinate frame like so. So we're going to have to write our tension as a vector. And then essentially all we have to do is compute the moment with which this tension makes around point B and around point O, and that will solve the problem for us. All right, let's get some lines in here to help us orient this tension. We have a line here that we can tell is perpendicular to this arm of the machine, and that's tilted at 20 degrees. So I'm going to put a line in here. Go with like this. That whole angle in there is 40 degrees, and if I look, then I can tell that this line, or this angle, is 20 degrees because that's equivalent to this one here. So this angle here must be 20 degrees. And this is a vertical edge, so it's like a y-axis. So at this point, we can write our tension as a vector. So the tension T is equal to 780, the magnitude, times the sine of 20 degrees in the I direction, and then minus 780 times the cosine of 20 degrees in the J direction. Again, what we're saying here is T sine 20 is a horizontal edge, so that's I, and T cosine of 20 is a vertical piece, and it's pointing downward. So that's a J-type component. And so T is equal to 267 in the I minus 733 in the J, and our units are newtons. So we've got our tension, and now we want to compute a moment. And let's get some force arrows here. We can think about this tension acting through point A back here. It would have a component like this, perpendicular to the arm, and then a component parallel to the arm. And the component that is perpendicular would be T times the cosine of 40 degrees, and then this component would be T sine 40 degrees. Now when I do the moment around point B, again we'll do this as a vector. If the x-axis is positive to the right and the y-axis is positive up, then the positive z-axis is out of the page. So, the moment around point B, well, this T sine 40 piece is going to pass through point B, so it will not contribute to the moment. I will only have a contribution from the T cosine 40 component, and that's going to produce a counterclockwise rotation around point B, which for me is a positive z direction or a positive k. So the moment around B is equal, the moment arm distance can be seen as this highlighted portion, which for us is equal to 381 millimeters minus 83 divided by 1,000. And then we multiply it by T cosine 40. And then if we substitute in, we have 381 minus 83 over 1,000 multiplied by 780 times the cosine of 40 degrees. And the moment around B, oh, and this is, this is a K vector. We have to put a vector sign here. Vector direction. We can't have moment B as a vector equal to a scalar, so we have a K here. So the moment around B is equal to 178.1 K Newton meters. Now I could have used X and Y components for this moment, and if you'll permit me, let me just sketch that really fast. I'll use a different color. So we could have a Y component here and an X component here, and I could have used that. This one is T sine 20, and then this is T cosine 20. And it wouldn't really have saved me anything because what I would have to do, the y component would make a moment around point B, and so would the x. Because it's so easy to get this perpendicular distance that I've shown here between A and B, and to use a component of t perpendicular to the arm, it's much faster solution if I would just use that. Now I would like to sketch the force couple that we've just drawn. So let me grab my red arrow again, and if this is my tension T, won't make it quite so long, then basically I can move this to point B. We can of course label this as T. We know this is 20 degrees right here, and then we can add our moment to it. Our moment is in the positive k direction, the way we've done this. So this is our moment around B. So that is the force couple system at point B. Now, I'm also asked to determine the force couple system at point O, and I'm going to start with the force couple system at B, and I'm going to use that because that will actually be a lot easier for me to do. Okay, so I want to find my force couple system at O. Well, the tension or the force is unchanged. I only have one force, okay? And we took this tension and turned it into another tension in a different spot with a moment. And so now I'm going to do the same thing. I'm going to take this tension and this moment, and I'm going to move them over here to point O. So obviously the tension will be the same. So I'll just move him over. All right, so there's my tension. The expression will not change. This is still a 20-degree angle. But now what I've got to do is compute the moment around O. And since I'm starting kind of almost there, it won't be too difficult. So the moment around O made by MB and this tension is equal to the following. Well, it would have to be MB. All right, we'll just add that moment. Moment is a free vector, so the MB is easily just moved over to point O. And then if I think about T, T has got two components, and if we draw those, we have one y component, and then we have an x component, and the x component is going to pass through point O and will not make a moment, but the y component will not pass through point O. It misses it by 127 millimeters, and by the right-hand rule, Ty would produce a counterclockwise moment around point O, which for us is a positive k direction. So we'll just put plus Ty times 127 divided by 1,000, and we'll just add that it's a k. So this is a vector expression. So now we can substitute the moment at B, 178.1 k, and then plus 127 by 1,000, and then Ty. We've actually already computed it here, but I'll write the general expression, 780 times the cosine of 20 degrees, and that's also in the k direction. Now, if we compute this number, we find that MO is equal to 271k Newton meters. Again, positive k would be a clockwise type direction if we were going to record things in that fashion. We're not recording in that fashion. And let me just sketch the moment really quick. The moment around O is positive k and looks like that. And there we have it. So we took a single force out here at A, and we turned it into first a force couple system at B, and second a force couple system at O. And all three of these systems are equivalent. They have the same effect on the system, and because we're dealing with rigid bodies, we're able to do this. And that's all we have for this problem.